All right, everybody. So this is our video on wave interference and standing waves and some other phenomena of sound. So in the last video, we talked about wave interference a little bit before, and that's just where waves overlap. And when they overlap, it's called superposition. And they're overlapping because they're in the same space at the same time. So if I had multiple waves, and we'll have some diagrams on the next page, but those waves, when they combine, they'll either add and make a bigger wave, or they'll add and make a smaller wave, and that's constructive and destructive interference. So you can see like waves being in a phase and out of phase. In phase means that the same parts of the waves are lining up together, and they're out of phase when they're lining up where like you have a crest lined up with a trough. So here's some interference patterns, and that's what we're talking about. So if we had two identical waves and they were right like in the same spots, like this crest and this crest would line up and make a bigger crest, and then the trough and the trough would line up and they'd make a bigger trough. So that's called constructive interference. And then if the opposite occurred, where you had a crest and a trough lining up together, they would be canceling each other out, or like destroying each other. So it's called destructive interference. So I've talked about that in other videos, and that's what's going on. So this is for transverse waves. The same thing happens in longitudinal waves. It's harder to see. So in longitudinal waves, we have our high pressure areas and our low pressure areas. So we have our compressions, where the particles are pushed together very tightly, and the areas where they're stretched out, which is the rarefactions. So again, if they're lined up the same way, where you have the compressions lining up with compressions, you get a bigger compression. And then if you have the rarefaction lining up with a rarefaction, you have a bigger rarefaction. So the same thing happens in that. So that's like the same idea of constructive interference, creating greater amplitude for longitudinal. And then C and D here are the destructive kinds. So again, they're canceling each other out, where you have a crest lined up with a trough, or a compression lined up with a rarefaction. So that when they line up, you get basically nothing. So that's the idea of interference. And interference can be useful in everyday things. So if you have noise canceling headphones at all, then what they're doing is that headphone is sending out a wave signal or a sound that is canceling out the crests and troughs, or the compressions and rarefactions of the other wave. So it is basically mirroring it exactly. So like this is a crest and that's a trough, and that's a trough, or that's a trough and that's a crest. So like they just match up what the wave is, like what it's interpreting is what it's putting out, and it produces basically a cancellation effect, and you don't hear things. So again, just talking about interference, we can do this with a demo with speakers, and as the speakers they're putting out sound waves. If you put them out in phase and you move them together, or out of phase, you get them to cancel each other out again, so you won't hear any sound. All right. So another interference phenomena that happens in lots of different things is called a standing wave. So a standing wave is one, and I have this a little bit over. A standing wave is one where the wave appears not to move, but that's not really happening. Like there's waves moving. They're just, because the way they are lined up, they produce this pattern where it appears not to move. So there's lots of situations. So it's guitar strings, columns of air. Most musical instruments use standing waves to produce sound. We're just going to focus on the strings because it's a little bit easier to understand. So we're going to do a demo in class where we're going to have a string tied from one end to another, like a post to a vibrator. So the vibrating mechanism will shake the string back and forth and produce waves on it. So like the thing is vibrating up and down and sending a wave, but what happens is the waves reflect, and then that reflection interacts with the initial wave that's being sent by the vibrating mechanism. And because of that, it produces standing waves. So we'll see standing waves in class. You'll have a view of that in person if you're there. If not, then it kind of looks like this. So you'll get these kind of bumps, kind of looks like a football shape, produced on a string, and that's what's happening with the sound waves in an instrument. It's the same phenomena. It's the reflection coming back and interacting with that incident wave, and the reflection and the incident wave are in the same patterns, so they keep producing the same standing wave form. All right. So so here's for some standing waves. There are some parts of standing waves that we'll talk about on the next slide. So they're called nodes and antinodes. So a node is a region where basically destructive interference is occurring and the waves are canceling out, and it's a wave where nothing vibrates. So it's like there's a point where it doesn't move. And then the antinode is the exact opposite of that because it's anti the node. So if it's a node doesn't move, an antinode moves the most. So it's like the amplitude, it's the constructive interference happening where it vibrates kind of the biggest space. All right. So and they just keep repeating each other. So there's a node, a node, a node where it's not moving, and then the antinode and the antinode, and we keep going if you had more than two standing waves, which is what you have in this picture. So a standing wave, again, I talked through these a little bit, node and antinode. Various factors affect how a standing wave is produced: frequency, the length of the string or the length of the air column that's being vibrated, and n is just the number of standing waves produced. So again, if you think about this is a point and this is a point, if we vibrate it, the fewest standing waves can just be one, so it would be like one football shape. So every football shape is a standing wave, so that would be 1. So that would be n equal to 1. That's the fundamental frequency. That's the lowest frequency. If you vibrate it at, so like whatever frequency you're vibrating at when it produces this pattern, that's the fundamental frequency. If you had the 2 points again, so another point, same 2 points and the same distance apart, but this time you got 2 footballs. So you can see that's like one complete wavelength. That would produce, and when it reflected back, it would do this. So you have 1, 2 standing waves produced on the same pattern. So that would be the second harmonic. So n equal to 2. For strings, this is the equation that we use. So the length is equal to, for the first one, the length of the string, which would be the distance between these 2 points. So if I drew in this kind of going across, that length going across would be equal to a half of a wavelength. For the second one, it's just the wavelength is equal to that string length. You could produce lots of different wave patterns on here, so 3, 4, and you could just keep increasing them. So that is the general formula for that. All right, so some other phenomena, particularly with sound and sound waves, is we have these kind of wave patterns that are produced. So we talked about like Doppler effect and the frequency and the observed frequency and stuff. So like if the source is producing a wave, so like if we just had a bug and it was like making a pattern in water, so it was like touching the water and making a circle kind of wave. If it wasn't moving, it would just be a circle, and the circle would move out. But if the bug is moving at the same speed of the circle, it's called a wave barrier. And there's like this wall of up front here, this wall of waves that is like one on top of the other. All right. If for some reason the object can go faster, so the bug can't go faster than the waves it's producing, but airplanes can, and other things can. So a supersonic aircraft is one that goes faster than the speed of sound. And what happens is it's going faster than these waves that are being produced. So the speed of the aircraft is faster than the speed of the wave of sound. So when that happens, you get these what are called bow waves that are produced. So a bow wave is this V kind of pattern. The faster you go, so like the faster this velocity of the object is, so the velocity, as the velocity of the source of the sound is greater, you get a narrower V. So like if it's going almost the same speed, it would be, the wave is flat. And then as this goes faster, it makes a V shape. And if it goes faster and faster and faster, the V gets more and more narrow. So shock waves are something that you may have heard of, and that happens when a airplane goes faster. I haven't heard them for a while because I don't think they produce them too much anymore. But at least around here, when I was growing up around base, I would hear some shock waves, or they would break the sound barrier. It'd be a sonic boom is what you would hear. So it's the same idea with the V pattern. So the bow wave, it's just in 3 dimensions. So it makes a funnel kind of shape instead of just a like a 2-dimensional V, but same concept. And it happens because there's 2 different pressure cones produced. So the pressure in front of the airplane is a high pressure cone, and then afterwards low pressure cone, and that dip creates that very loud boom that you hear. All right, so that's what happens. Other things that are basically a sonic boom, if you crack a whip, it's the same principle. It's that quick, like the object is moving faster than the sound, and it produces that very loud noise. All right, some other phenomena with sound that you guys are probably interested in. We talked about reflecting and refracting before, but if you have ever gotten an ultrasound, or if you're into doing those kind of scans, if that's what your specialty is going to be, then you are using refraction. So the way of light bends differently. So the reflected, it looks different when it hits different types of materials. So the density of the baby here in this ultrasound is going to make it appear different. Okay, so they can see the sound waves bouncing off of the different substances in the object, and that's where they can kind of outline the baby's head and body and things like that. Another phenomena that uses similar principles is dolphins and what's called basically echolocation. So they emit a sound wave, they kind of chirp, and they send a wave out, and then that wave reflects back to them. And we did this with our sound motion detectors if you were in person in class. So we use these sound producing sensors that would click, and those clicks would bounce off and then reflect back. And based on the time it took for that reflection to come back to the sensor, it could tell how far something was away and how it was moving, and it could interpret all that information. And dolphins do that automatically. Bats do it as well. Okay. The last thing we're going to talk about is resonance and vibration. So with vibrations, things vibrate, and we know this already. And a force vibration is just when you hit something and it vibrates. So if I took a tuning fork and I smacked it on the table or on a stopper or something, then it would vibrate. Other things vibrate, there's just like a vibration that happens when you hit it. Okay. A natural frequency is like a frequency which is within an object. It's based on the shape of the object and the elasticity. So like that tuning fork, I made it vibrate, but there's the way that it is designed or the way that it is built, it has a natural frequency. So everything has this natural frequency. They're not all the same. And if you make something vibrate at its natural frequency, it resonates. So resonating is a phenomena where you are making the vibration happen at the natural frequency. So some examples of this, like a swing. So like if you have a resonance, it's like, okay, so something's swinging back and forth. Somebody's at a swing set and they're swinging back and forth, and you push them at the exact right moment. Your forced frequency, which is the push, is matching that natural frequency. That is the vibration that it's swinging back and forth at. And then when that happens, what happens is that object vibrates more. So you are basically adding to the amplitude, and the person swings higher and higher and higher. In sound, this happens with like opera singers. So if you've ever seen the phenomenon of like an opera singer breaking a glass, so like they sing at the proper frequency that matches the frequency of oscillation, the natural frequency of the glass, or like champagne glass, and it actually breaks the glass. Tuning car radio stations work the same way, troops marching over bridges, things like that. One phenomena that has happened before, and I would suggest you just Google the Tacoma Narrows Bridge. This happened from resonance. So I'll try to bring it up real quick. Hold on, let's see if it'll come up through this. So so this video is, try to skip it after the 5 seconds. Okay. Is basically a bridge. I think it was in Oregon, and it was across a gap. And what happened was they built the bridge, and you can see there's all these strings, the suspension bridge, and the air with the wind would vibrate, and this bridge, this is all concrete, would oscillate very violently because of the natural frequency. So they built this bridge, and then obviously like it didn't stay working very quickly. People couldn't go across it because it was too dangerous when the winds were at the right frequency. So eventually it did collapse. So these are videos of it, and it's pretty crazy. You can see, imagine, like, this is road, this is concrete that is vibrating up and down violently like this, and eventually it breaks, and like these cords break and the road breaks and it falls. So I don't think anybody was actually hurt in the collapse. There was a car on there when it finally did collapse, and you'll see there's like a person who runs out. You'll see them kind of get out of here if you keep watching it. So resonance is a real thing. It can be dangerous, so you just got to be careful with it. So those are some more phenomena that go along with sound. So that was standing waves and resonance, and then kind of like the bow waves and shock waves and things like that. So I'll stop there, and hopefully you have a good day.